Okay, everybody, we're right on the brink of spring break, so today's going to be a big day. We're going to be covering the most important sensor today that you're going to be using for your robots. One of the most important sensors. I can't say that one sensor is more important than the others, but this one is going to be the distance sensor. So this one tells you how far away an object is in front of it, right? So of course this is like the robot's eyes, right? To tell whether there's something in front of it or not and whether it has to avoid it. Okay. Or turn, or it can be used for a number of things. You can use your imagination and be creative on it. So what I want you guys to do is pull out your lab notebooks now. You really do need to take notes this time on this stuff because we're going to use it over and over again. So make a new entry in your table of contents for the next page that's available. Then on the title, I want you guys to put down ultrasonic distance sensor. So we're now in course 2. This is the second lesson of it. And we're going to be covering this device here, which is ultrasonic distance sensor. So we're doing sonar today. Pretty fun. And this is the same sonar that the boats use, submarines and everything. So you guys can get a heads up if you want to work for anyone using sonar technology. Okay. So I can wait for everybody to get caught up with their notebooks. Does everybody have their notebook open and ready? Yes? Notebooks? Got it? Okay. Daniel, good? Okay, awesome. Alright, so ultrasonic distance sensor. So we're doing sonar today. Okay? So, the basic principle of sonar is that you send out a sound. Okay? So instead of like your eyes are reading reflections of light. A sonar uses sound. So what we do is we send out a sound wave with a speaker, and then we let it bounce off of an object and come back to us and we receive. Okay? So in this sense, we're using sound to see things. Okay? So this is the basic principle of sonar. So we have a transmitter here, and we have a receiver. So the transmitter is going to send out a sound wave. The sound wave is going to hit an object, bounce back, and then we're going to receive it over here on the receiver side. Okay? The sound sent out, we usually call it a ping because it's going to be a short pulse of sound. So we're going to send out a pulse, right? The pulse is going to move, it's going to hit an object, and then the pulse is going to return, and we're going to measure how long it takes for it to get back to us. Okay. So, does anybody have any questions on that? On the basic principle of it? Yes.
So it's kind of like it's kind of like you're seeing with sound, like you're bouncing off something, you see it like how like dolphins and bats use it.
Exactly. Yes. Yes. It's exactly like that. It's like dolphins or bats. I was actually going to ask that question. Holm suggested that I ask that question. Anybody else have any other practical applications of sonar? So we got dolphins use it, bats use it. What else uses sonar?
We use it to make like a 3D, like to figure out the shape of something.
You could probably use it to figure out the shape of something. It might need to be a little bit more advanced than just this simple sensor, but yes. Anybody else? Okay, great. All right, so sends out a ping, it hits the wall, it comes back. We measure the time it took for the ping to go out and come back, and then we use that time information to figure out how far away the object was. Okay. So, what are the important things that we're going to need to know for to use this sensor? What about the speed of sound? Okay. So let's start off with a car example. Okay. So we have a car here. You see the car? It's a cute little like smart car thing. Okay. So let's say the car is going 30 miles per hour. Okay. That would be the same. If we can convert that to meters per second, right? Would be 13.4 meters per second. Okay. So this is this is kind of a simple thing, right? So if my car is going 13.4 meters per second and it travels for 3 seconds, how far did my car travel? So we know that it goes 13.4 meters in 1 second, right? Which is what 13.4 meters per second means, right? It's a rate. Speed is a rate, right? So all we do is, if we know that we traveled for 3 seconds, we multiply the speed times the time, right? To get how far it went. Okay. So now let's think about it in terms of sound. Okay. So sound has a fixed speed in air. It actually changes a little bit if you want to be more precise, but for all of our purposes, it has a fixed speed. Right? Okay, so that speed is around 761 miles per hour. Pretty fast, right? Pretty fast. Sound. Okay, and that's about equivalent to 340 meters per second. So if a sound wave were traveling for 3 seconds, how would I figure out how far it went? Right, you'd multiply it, right? Okay. So let's think about some of the other things that we can notice, right? What about lightning strikes? You guys have seen lightning strikes?
Yeah.
Yeah,
So
right.
you would have to times speed by rolling sound.
Okay, so the thing about lightning strikes is light travels way faster than sound. Way faster than sound. So we see the lightning first, right?
Yeah.
And then several seconds later we hear the sound. Why is that? Yes.
Because light is faster than speed, so the speed takes a little bit of a while to catch up with the speed of light.
All right, good, yeah. So the light's traveling, it hits our eye first, right? And then the
Right.
sound is traveling behind it at a slower rate, right? So we can figure out how far away that lightning was by counting the number of seconds, right? And then it should be 340 meters every time 1 second passes.
Okay.
Right. Okay, so that's the concept. Okay, so I noticed that in a lot of our other activities, this was a recurring kind of issue for a lot of people, and I think that this continues on all the way until you hit your university. A lot of my students have this problem, and I think that it's something that we can get out of the way now because I think that you guys can get a good handle on it. It's called dimensional analysis, okay? So when we measure things or whenever we want to apply math to the physical world, we want to use units, right? So units would be things like inches, feet, meters, right? If you're talking about distance, what other kind of units would you have?
Lights.
Light, yeah, lights, I guess so. That's a unit. Doesn't have to be distance. What other kind of units would you see? Grams, pounds, yep. Hours, seconds, yes. These are all units, okay? Okay, so whenever we're doing a calculation, a lot of times we're doing a calculation with the intent to figure out some sort of measurement, right? So we need to make sure that at the end of our calculation, we end up with the correct units, right? So this is a distance sensor. Can anybody tell me what units I would want after I finish my calculation? Distance. I want distance. Sorry, I know it seems kind of like a dumb question, right? Well, yeah. We're gonna take a look at that in a minute. But you're on the right track. You're ahead of the game right there. Good job. So we want distance. So when we want distance, it can be in any of the distance units, right? So meters, miles, feet, inches, whatever distance we want, but we need to be able to calculate that, right? Okay. So I'm gonna ask a lot of questions that you guys might be insulted by. What's 1 divided by 1? 1, okay, good. How about 2 divided by 2? 1, okay. 3 divided by 3?
1.
Okay, so what happens if I multiply 1 times 1 times 1?
Always one.
You guys might be wondering why I'm asking all these silly questions, right? Everybody knows this, right? What if I mix it up? 1/3 times 2/1 times 3/2.
Also one.
Also 1, but why?
Because multiplication, they're always equal no matter how you multiply.
Oh, there's a rule for that. What's it called? Like you can move around any of them in space.
Good, yeah, that's exactly what the rule says. I think you're looking for the technical term, 'cause I know you're a technical guy, right? So it's a commutative property.
Oh yeah.
Yeah. So that means that I can rearrange them and it's still going to be the same, right? So addition has the commutative property if 1 + 2 = 2 + 1, and so does multiplication, 2 times 1. Okay, so now that we looked at this with numbers, I'm going to change it up a little bit. So now we can look at it with units, okay? So if we introduce units into the calculations, nothing changes, okay? So this is really, really important whenever we're doing calculations, whenever you're taking measurements, and whenever you're analyzing data, okay? So the units are super important. You should write down the units every time that you write down a measurement. When you do a calculation, you should include the units because they can be used in the calculation just like a number. So if I said inches divided by inches, that's the same thing as 1 divided by 1, okay? So in this example, we're taking the same thing that we saw on the last slide, and now we can see. You guys might be maybe laughing at my bad handwriting here, but I try my best with it. I needed to write it fast this morning, so can everybody read it? It says seconds, inches. Yeah. Okay. Right. So it has the same thing, the commutative property, right? So if I said inches times seconds times meters divided by meters times inches times seconds, what is that?
1.
Okay. So there's two things that you guys are gonna see a lot in your science careers from now on, okay? A lot of the tricks that the math people use are adding 0 to something. So adding 0 to something is actually super powerful. You can solve a lot of equations by adding nothing. So what that means is sometimes I'll add an amount to an equation and then I'll subtract the amount from the equation, the same amount, right? But if I add and I subtract the same thing from the equation, then I'm actually not doing anything to it. But if I do that, sometimes I can rearrange and it becomes magical and then I can solve the equation now when I couldn't have solved it before. That's one of the tricks. The other trick is multiplying something by 1. What happens if you multiply something by 1?
Equals 1.
It stays the same, right? So in effect, it doesn't have any, it doesn't change my value, right? So I can multiply a value by 1 and it should stay the same, right? Okay. So let's take a look at what we can do with this, right? So 3 seconds is also equal to 3 seconds divided by 1, right? I can say that, right? So what if I said 3 seconds divided by 1 times 340 meters per second? What happens to the seconds? It cancels out, right? And then what do I end up with? I end up with meters left, right? Because the seconds go away. Because seconds divided by seconds, do you see this over here? So right here, you have seconds divided by seconds, right? And so seconds divided by seconds turns into 1. And that's where it disappears. And then now I have 3 times 340 times meters times 1. And I end up with meters. Okay. So I'm going to ask another dumb question. What? So 2 equals 2, right? Okay. So if I divide both sides by 2, what happens? I get 1 equals 1, right? Okay. Very simple. All right, so now we're going to take a look at something called the conversion factor. Okay. We have distances, right? So we have meters and feet. We all know that a certain number of feet equals 1 meter, right? So you can turn that into an equation. How about inches and millimeters, okay? So 1 inch equals a certain number of millimeters, right? So 1 inch equals 25.4 millimeters. These are equal, right? Okay. So now what happens if I divide both sides by one of them, right? So I could divide it by millimeters or inches, right? So if I divide both sides by 25.4 millimeters, what do I end up with on both sides? So take a look at the top one here, right? So if I have 2 equals 2, I can divide both sides by 2, right? And I end up with 1 equals 1, right? If I take this one, 1 inch equals 25.4 millimeters, and I divide both sides by one of these, both sides end up equaling 1 in the end. Okay? What that means is 1 inch divided by 25.4 millimeters is going to be equal to 25.4 millimeters divided by 25.4 millimeters. What is 25.4 divided by 25.4? That means 1 inch divided by 25.4 millimeters equals 1. So that means that I can multiply anything by 1 inch divided by 25.4 millimeters, and it's not going to change the value. Okay? So here's an example of this. So I measure 10 millimeters. Okay? So I get my ruler and I measure 10 millimeters. Okay? And now I want to know how big that is in inches. How do I do it? So I can multiply it by 1. Because if I multiply 10 millimeters by 1, I still get I still get 10 millimeters, right? But if I want inches, I want the millimeters to cancel now, right? So take a look at this. So 1 inch over 25.4 millimeters, we know is equal to 1, right? So I'm going to use that trick. I'm going to say 10 millimeters times 1 equals 10 millimeters, right? So 1, I can multiply anything by 1 and it's still going to be the same, right? So now I know 1 inch divided by 25.4 millimeters is equal to 1. So I can substitute that back in here, right? So now I get 10 millimeters times 1 inch divided by 25.4, right? And I get millimeters on the top and millimeters on the bottom. What happens to them? I get millimeters divided by millimeters, which is 1. And then I get, what's left? Inches, right? Okay, so you guys are going to use this today, hopefully, to figure out what the distance is going to be. So let's take a look at this sensor again. You guys like my drawings? Yeah. Yeah? Can you identify what that is? What's that?
A wall.
This one's not a wall.
Speaker?
It's a speaker, okay, good. It's a speaker. What about that one? It's not an ice cream cone.
Microphone.
It's a microphone? Yeah. Okay, good. Yeah, it's a microphone. I did my best. Okay. I'm not that good at art, obviously. Okay, so the wall. Okay, so this is the sensor here. Okay. So I got a speaker and a microphone on it, right? Okay. The speaker is going to send out a ping at 340 meters per second. Okay. It's going to travel and hit the wall there. It's going to bounce back from the wall because sound waves reflect. It's going to bounce back and then it's going to hit the microphone. Okay, so I'm going to have 2 time periods here. I'm going to have time 1 that it takes the sound wave to travel to hit the wall. Okay. I'm going to have time 2 that it takes for it to come back. So when I measure the time it takes, right, I'm getting both time periods, right? So if I send out a ping and then I receive the signal and I get a measurement, what time am I measuring?
What time to travel there?
The time to travel there and back. Okay. So I get both travel times, right? I'm interested in distance, right? I'm interested in distance here. This is what I'm looking for. This is a distance sensor, right? So I'm looking for this value here, D, right? Can anybody immediately identify how to figure out what D is? if I knew T1, T2, and the velocity of sound?
Times total divided by 2.
So what is it?
Velocity to sound is total time. Yeah.
Divided by 2. I heard that.
Or just times time 1, right?
No, you had it right the first time.
Oh.
If you had time 1, then you would be able to do it, right? Yeah. So that's what it is, right? So distance is going to be the velocity of sound times time 1, right? Or the velocity of sound times time 2. We don't immediately know the velocity of, and we don't immediately know time 1 or time 2, right? But we do know 2 time 1. Well, we know time 1 plus time 2 is the time total that this thing's recording, right? So we end up with 2 times the distance if we just took the total time times the velocity, right? And we just divide it by 2, like you said, right? Okay, and then we end up with the equation that we just came up with. So this is important. Are you guys writing this down? You need this equation. Here. I can wait for you guys to write this down. Let me know when everyone's finished. So if you have a formula and equation, you need to know what all the variables in it are. So in this equation here, we're going to have Vs, which is a constant, right? Which is the speed of sound. So the speed of sound is 340 meters per second. Okay, good. We're going to have a measurement value, which is going to be T total, right? So that's also going to be a known. And then I'm solving for D, which is the unknown. Is everybody ready with that? Okay, good. Okay, so we know the velocity of sound in meters per second, but sound travels really fast, right? And this thing is obviously only recording a short distance away. One of the things about a microcontroller or a digital device is it only deals with whole numbers because of the way that it's built. It's built with switches, which is 1s and 0s. So internally it's only dealing with whole numbers. So what it's going to do is it's going to give us a whole number of microseconds, so that we get a more accurate measurement, right? So this thing is going to record and send us back the number of microseconds it took for the ping to travel and come back. Okay, so having the speed of sound in meters per second is not as helpful, right? What would we want? We want the velocity of sound in meters per microsecond. So what we're going to do is we're going to create a conversion factor, right? So remember our talk about creating a conversion factor. So just like 1 inch over 25.4 millimeters, we need a conversion factor for meters per microsecond, right? Okay. So how do we do this? 1 microsecond equals 0.000001 seconds, right? So we can divide both sides by one of those numbers. Which one? Which one do we want to divide it by to get our conversion factor? So one of the rules of thumb is which unit do we want to end up with on the top? Meters. Okay. Which unit do we want to end up with on the bottom? Microseconds. Okay. So our conversion factor is going to have microseconds on the bottom, right? So that helps us to decide which one to divide by. Right? So we're going to divide by microseconds. And we end up with a conversion factor of 0.00001 seconds over microseconds. And we can multiply that by the velocity of sound to get the speed of sound in meters per microsecond. So when our device reports to us the number of microseconds it took to go and come back, then we can just multiply it directly by the speed of sound in meters per microsecond, right? And then we're going to end up with what? So we have the time in microseconds, and we have the velocity in meters per microsecond. If I multiply the two together, what do I end up with in terms of units? Meters. Okay, good. Perfect. Okay, so here, can everybody read my handwriting? I know I keep on asking, but okay, good. Okay, so this is what they call a block diagram. Okay, so this is every programmer's friend. This is how you start a program. This is how you plan a program, and this is basically how you structure a program before writing it. So this is almost what they call pseudocode. You put this together to look at what the flow of your program is going to be in terms of functional blocks. Okay? So if we see here, what we're going to do is we have start, right? So the microcontroller has to start somewhere, right? Starts at ground zero. So remember in our Arduino code we saw that there's a setup script, right? What's special about the setup script? It only happens once. Okay, so we can see here that we start and the arrow comes down and it never comes back to it, right? So there's no loops going on in the setup script because it only happens once, right? So the first thing that we're going to do is we're going to open the serial port. The next thing that we're going to do is we're going to set up the pins in order to be input or output, right? After that, we're done setting it up for using this. Okay, here's the important part. Now, right after we get everything set up, now we're going to send a sound pulse out from the device, right? So we're going to program that in, send a sound pulse. Okay. Then we're going to create variables for total time and distance. And then we're going to record the total time that it took for it to bounce back and hit this, right? And then from there, we're going to do the calculation to figure out what the distance is. So I'm going to start reviewing some of the main functions that we use in Arduino. I know that there's been some confusion and some trouble in using them for some people, so I'm going to go over them again. Okay, so serial connection, right? What's a serial connection? So it's one type of communication. Serial uses single lines to transmit data bit by bit, one at a time on a single line. So this one has a receive and a transmit pin. You're sending the signal in one direction on one pin, and you're sending it on the other direction on the other pin. Right? Okay. This is super important. The serial connection allows you to communicate bidirectionally with your chip that you're programming, right? So we're going to use this later when we program with the Raspberry Pi, because we're going to use the serial connection in order to communicate with the Raspberry Pi. It doesn't only allow you to communicate with the chip directly over your console, it's going to also allow you to program another computer to interact with your chip. So this is going to be the way that they communicate with each other. So when we program it, we say serial begin 9600. What that means is we're going to begin the serial port connection at 9600 bits per second. And then when you open your serial console, you have to make sure that you set your port properly. And later on, when you do your Raspberry Pi, you're going to have to make sure that when you open the port, it's still at 9600 bits per second. And then we've seen the serial print. That's how you send data over the serial port to whatever is on the other side of it. Okay, pin mode. So you're going to need to set your device up and tell it what you want its pins to do. So you have to tell the device whether a pin is an input pin or if it's an output pin. What can digital pins do? Can everybody tell me? So what can a digital output pin do? Yes.
Send a 1 or 0.
Perfect. Can send a 1 or a 0. Right. So 1 in this sense is going to be a 5-volt signal. So if I say digital write high, that means make this pin output 5 volts on it. If I write digital write low, sorry, this is the right slide. Please tell me that I'm not on the right one. Okay, so digital write high means output 5 volts on this pin, right? Digital write low means output 0 volts on this pin. Okay. So what about an input pin? What can that read? So it can read a 1 or a 0, right? Just like Daniel said. So if there's something close to 5 volts on it, it's going to read a 1 when I say digital read pin 3. If there's something close to 0 volts, then it's going to read a 0 if I say digital read pin 3. Okay, here's the meat of this project. Okay, so sending a sound pulse. All right. This is a digital sensor, but you need to understand how to use it. Okay. So in order to make this thing send its sound pulse, it goes through a certain sequence. So the first thing that it needs to do is you set it low. You set the pin on what they call the trigger pin here. So you're going to provide power to this device, so 5 volts and ground. And then you're going to connect the digital pin to the trigger pin. First thing it needs to do is get set to low. You need to hold it low for 2 microseconds. So 2 millionths of a second it's going to be on low. Then what we're going to do is we're going to trigger it, we're going to turn it high. Right? So we're going to put a pulse on it, 5 volt pulse. And we're going to hold that pulse high at 5 volts for 10 microseconds. After the 10 microseconds, then we're going to write it back to low. So basically what it looks like is a square wave, right? So you guys have seen this one where it's 0 volts, it goes up to 5 volts, it stays at 5 volts for a little while, and it comes back down, right? That's our pulse. So if you can imagine that pulse being sent to this, it sends out a sound wave during that pulse, and then the sound wave is going. All right? Any questions on this? No? So we're going to use the digital write function and the delay function. So the delay function just means wait for a little while. In this sense, we're going to delay for some microseconds, so millionths of a second. All right. Reading the time. Okay, here's the other thing that you need to do, right? We're going to use a function called pulse in. Okay. So pulse in measures the time until the pulse, a pulse is returned to the digital input pin, right? So just using this function right here, you can use some sort of variable there. So we're using int duration here, and then set it equal to pulse in. The pin number that you're using for what they call echo on this. So when it receives back the pulse, it's going to send out the correct signals for the Arduino to read how many microseconds it took for the pulse to travel and come back. Okay. Okay. So how many people have their sensors?
I already got one.
So I gave them out last time. Hopefully people brought it.
I never
Yeah,
caught
you have one, okay. No? Jaden, do you have one?
My dad's far out.
Okay, you have one. You don't have one. Esther has one.
nobody.
Daniel, do you have one?
No.
Do you have one? Okay. Okay, so what we're gonna do is for the assignment for today is you're gonna connect and program your Arduino to just read the distance, and then I've assigned some assignments on the Google Classroom. Sorry, I forgot to put the assignments up last week, so it was hard for you guys to turn it in. This time I put it up so that you guys can turn it in. I kind of want you guys to submit them on the Google Classroom this time. So you have three assignments since we're not going to be here for a while. So the first one is going to be for coding. I want you to set up a circuit that lights up an LED when you get too close. So basically it's just like the same thing that your backup sensor on the car does. Oh, you're too close to something, stop, right? Okay. This is the same technology that your car is using, by the way. And the second one is you're gonna be a writing assignment. You just have to write a short paragraph, nothing super long. Please turn that in. And the third one is I need you guys to start using fritzing and create the schematic diagram. I know that we went over this a little bit. There's tutorials online. I want you guys to keep in contact with me over Google Classroom. Ask me lots of questions on this. If you get stuck trying to do your schematic, and I'll walk you through it. Okay. So we're gonna have 2 or 3 weeks of break. So I want you guys to really work on finishing these assignments. don't really want to do the next activity until you guys finish this. So I want everyone to really work hard and get it done. Okay, I think that you can do it. All right. So I think that's it. Kelly and Daniel, you can work together on this sensor. Okay.
Oh, that sensor. I don't have it.
I know I gave out about 4 of them last week.
I didn't get.
He wasn't here.
Okay.
I was here.
This one. So you guys share. We have one with Felicity. Should have a couple more. Okay, get to work, guys. Can you help me find some more sensors?
Yeah, I was.